Hello everyone, this is Anish and today I'm presenting a talk on ret2csu. This is like a new exploit technique that I just stumbled upon while trying to solve some CTF problems. I found this technique pretty nifty because it doesn't have a lot of limitations, to be honest. If there is a binary compiled with libc, then you can definitely use this technique in most of the cases. Uh, And so today's agenda is going to be discussing what ret2csu is, but to get there, we'll have to discuss a bit of other techniques and why they are not enough to kind of beat today's exploit mitigations. So yeah, just get started. So what is a Rop chain? A Rop chain is kind of an exploit technique which is used to hack buffer overflow vulnerabilities. Obviously there's the Frax article in 1995 suggested that we would write a shell code to this to some variable in the stack and then like leak that address and then jump to that address, right, using buffer overflow. But that technique doesn't really works because of some of the exploit mitigations that I'm going to discuss. But so ROP was kind of this was the kind of birth of ROP, where attackers were trying to hack these programs, but after NX and ASLR and code signing were like kind of introduced, they had no way to exploit buffer overflow vulnerabilities, and that's when they kind of discovered, or someone might have tried to exploit a ROP, exploit using ROP. So yeah, today's exploit mitigations look like this. So you already have the stack not executable in mostly like 99% of the programs, and ASLR is always enabled in most of the recent OSs. So NX just means that stack is not executable. ASLR makes your address space layout randomized. So whenever you look at a program, if you debugged a program ever, you would see like there are functions in that program. That's the in the text segment, that's like the local code that you've written. But if you use like some libc functions like scanf, printfs, or these, then you can see that they go through a calling. They have a specific way of calling those functions, and they use stuff like plt and got tables, and then jump to a address in libc. And the libc is kind of like common for all of the programs, and you have one libc in your system usually, but you can obviously use ld preload to change libcs and stuff like that. But yeah, so ASLR kind of makes it hard to guess the address, what address is your function or your libc loaded at. Stack protector makes it harder for you to overflow without kind of calling the stack protector function. So stack protector just pushes a secret value at the start of the function when the stack is kind of getting created. So it's at the base of the stack, and whenever you overwrite, I mean it's at the yeah, it's at the base of the EBP, and whenever you overwrite, the return pointer is just after that. So you'll have to override the protector cookie, and obviously at the end of the function, they're gonna check if the cookie is changed or yeah, fiddled with, and then they'll alert, or they'll crash the program. So that was one of the experimentation that was done to make it even harder to get EIP overwrite after Stack Overflow. And so to bypass that technique, even ROP cannot really do anything about it. You'll have to leak the stack cookie anyway, and then just incorporate that into your exploit. Then comes Relro, which is relocation read only. So I talked about briefly what is PLT and GOT. So these are these two tables that are used to call libc functions. And if you just disassemble your program that you compile, you'll see, and we'll also go through it in the demo later. But just to give you an idea, so relrow means that these GOT table and PLT table entries are read only, so you cannot write anything to it. So imagine a scenario where you have like any write what primitive. So you can write at a got entry of puts and change it to some other functions. So whenever a programmer would call puts in his code, some other function would be calling. So that's like That's how you kind of hijack the program's execution flow sometimes. And then the fifth one is PIE. PIE is kind of like a game changer for most of these exploits, because it really is kind of hard to develop an exploit with PIE binary, because PIE randomizes the code segment also. So, and yeah, we'll see how it looks like in a sample program. So for our first demo, I have created a simple program. It uses two libc functions, puts and gets, and it just takes input into a buffer which is size of 80. And yeah, it has no ways to check this when the sizes gets overwritten. So gets just is notoriously known for this. It's a common buffer overflow problem, basic one. So we can check out how it looks like in a debugger. uh, This is how main is defined. You can see that there are two calls to gets and puts, which are to this 400 address. So let's just try to see how the calling convention looks like for these libc functions. I'm just going to run the program, set up a breakpoint at the call. Uh, we can see that we're going to call puts, and RDI should be here. It has buff, so everything's accurate. RDI is the first argument, so yeah. And now we see that it's going to jump at this keyword pointer, which means it's going to jump at this address pointed by this address. Yeah, so you can see that, yeah, this is how it looks. So this is the puts address in libc, and we can see that it's accurate. They're just gonna jump there and print our thing. We can also see the security restrictions on this binary by just typing checksec, and we see that NX is enabled and rel-row is enabled, but there's no canary, there's no PIE, or there's no fortify. So to start with, let's just execute the program here. First of all, we have to disable ASLR. So we disabled ASLR, and this is just works on one shell. So make sure that you disable ASLR if you launch a new shell. And now we can check what's the process ID of this. So this would just give you where the memory, what does the memory maps look like for this binary. So we can see that libc is loaded at the base here. So now we know like how the program works and what's the libc getting used and where it's loaded. So all we need to do is to make an exploit is just to fill in the address of where the system would be, the system call in libc, and where the bin sh string would be, and we just need to jump to these addresses and do the job. So this is the exploit that I've written for it. You can see that I'm using pawn tools. Pawn tools is very helpful in these scenarios. I mean, it's not doing anything magical, but it really has all the tools needed to create an exploit. So I've already copied the libc that I was using for this activity in the repo and in this directory. So we can load the libc using this elf, which is also given by pawn tools, elf construct or whatever. And then using this we can also set up the load the base address. So for my system, as we checked, this is the base address that we got from psox, got from proc mappings. And the system address is this is just trying to find the system address in the libc. So you can also get it using readelf or some other tool, but Pontool just makes it like simple, and you can just write it in Python and in plain English pretty much. Then it's trying to find a reference to bin sh. So usually libcs will have a sequence of bytes which resolves to bin sh string, and it just gives the address of that, and it just prints the different addresses that we got. uh, and this is the ret. This is a gadget that we're going to use to make sure we don't get into some alignment issues, because so this is kind of like it happens in the newer versions of Linux. But if your Rop-chain is not working, it might be because your stack address or your XMM register address is not a multiple of 8. So to do that, we can call ret, and that fixes it up. So if your exploit is if your option is not working, it's a good idea to just add a ret someplace and just test it out once. So this is the ret that we're going to use. It doesn't do much besides that. So this is the exploit. So we saw that the buffer was 80 characters in size, and the next 8 characters are going to be RBP, which we don't care about for now. Then we have this pop RDI gadget. This is the pop RDI gadget we got from Ropper. So let me just show that. So Ropper kind of gives you all the different gadgets that you need to create a Rop chain, but it doesn't include all of them. But yeah, it should give you some basic gadgets that you want to, and like you can probably use it to develop most of the ret2libc and ret2plt exploits. So you can see that these are the complete list of gadgets. There are a lot, and I wanted to check for only RDI, so I just grep RDI and I can see a pop RDI gadget. So I want to control RDI because I'm gonna jump to system, and system only takes one parameter, which is gonna be in RDI. So I need to fill RDI with bin sh string in my exploit. So you can see that we got the pointer of bin sh from the libc here, and then we are just making a Rop chain by setting up pop RDI, after that bin sh, after that a ret to just kind of align the stack, and then a call to system. We can see how it looks like. I've set up a checkpoint so that we can walk it with a debugger on the side. So let's just, yeah. So this is the current, yeah. What is the process ID? It's 3015. And let's just set up a breakpoint at like the last ret in main. That's where our Rop chain will begin executing. Just press continue here, and we are off. All right, so we're at main here, and we've already received the malicious input in the program, and now we are at the stage where everything you can see like what really happens. So we're at the last ret in main, so whatever the top of the stack is going to be put in the RIP, and just it's going to jump there basically. So I step into it. I can see that my pop RDI gadget is getting executed, and whatever is on the top of the stack is gonna put into RDI. So we have the bin sh string on the stack, which is all good. Then whatever next is on the stack, we're gonna jump there. So right now we are jumping to our ret to make the stack more aligned, or if there is an issue, it would solve it. Yeah, we are at ret now, and now we can see on the buffer on the stack we have the address to system next. So we are gonna ret to system now, and we can see that RDI is properly set to bin sh. So we can just continue at this point, and here we can see that we have a shell. So system did get executed uh, with the bin.sh, and it's just running bin.sh for now. And as I was root at running the binary, I'm root in the shell as well. So we have just looked at the first scenario. This is the popularly known as ret2csu attack, where you know the libc file, know the libc version, and ASLR is disabled. So we see that NX and relro has like no effect on libc. Libc is working. So ASLR might make it harder, but it still works without ASLR being enabled or disabled. So this is how we basically know the create like exploit for ret2 libcs. So libc is known and ASLR is disabled. That's the assumptions. And so we execute the binary and like check the proc PID maps. We copy the libc base, and once libc is known, the exploit is simply to return to RDI, return to system with like RDI is equal to bin.sh. So yeah, we have like bin.sh. We just went over the exploit, so we saw that libcs have bin.sh mostly, and we can use like pawn tools to find offsets to these addresses. Also, you can use read ELF or something else. And we also need a pop RDI gadget, which we grab using Ropper, and then this is how the exploit looks like. So for the second case, we're gonna go with similar restrictions, except ASLR is gonna be enabled, and we have no libc version this time, and no libc is provided, and ASLR is enabled, which is on 64-bit Linux. So let's jump into the demo and like try to see how to exploit with ret2plt. So for this particular demo, we have the same program. The only difference is ASLR is enabled. So let's just set it to 2 for making sure that it is. And this program works the exactly same way, so we don't need to go into specifics. We can just directly jump in the exploit. So the difference is that we don't have libc's version, we don't have the libc file, right? And those addresses are going to change anyway every time, and the offsets are not if the libc is constant, but the addresses are going to change. So we need to leak, and then we need to figure out we need to leak at least 2 addresses to figure out what libc is being used, because in this scenario we assume that the libc version is not known. So yeah, to start with, this is how the binary looks, the main looks. We have the puts, we are referring to the PLT and GOT entries here. Again, we are using the ELF construct which pawn tool provides, and we can just get offsets to PLT and GOT entries for any function that it uses. So I've saved puts got and gets got and puts PLT here in these variables. And then this is just address to main, so that after our first phase of the exploit is gonna run, we're gonna jump to main back, so that we have another primitive to write, so that after we get our leaks, then we'll use those leaks to jump to system, right? So this exploit works in 2 phases, it's not only 1 phase anymore. And this is the pop RDA gadget which we get from Ropper the same way. This is the data segment which I'm not using right now. Alright, so like we can just run the exploit and debug it to understand it better. So let me just run the part 1. Part 1 just contains the first phase. So it just got to leak and exit for now. Okay, so yeah, we are here attached to 3701 main. Do the same breakpoint at main, the last ret main. Alright, so we can see that we're gonna jump to the pop RDI gadget. Let's jump there. We can see the top of the stack is puts got entry, so it's just gonna fill that in RDI. and now we have jumped into puts with RDI's value. We've jumped into puts PLT, and RDI's value is this, which is got entry of puts. So we're gonna get the leak of this address basically, and for every different execution this address is gonna be different. So that's why we have to, in the same execution cycle, we have to get the leaks as well as use those leaks to exploit as well. We cannot restart the program and then use the same addresses because ASLR would randomize it on every run. So yeah, so right now we're just printing out the got table entry so you can see that we get some leaks out, right? So now it jumped back to main because in our Rop chain uh, we have defined that. So we are jumping to pop RDI first, then we are setting the puts got entry into RDI, then we are jumping into puts PLT, and then we are doing that again with gets got and puts PLT. So it's gonna print out two addresses, puts got and gets got, and then it's gonna finally go to main, right? So we can see that the leaks are working. All we need is we need to parse it in our program. So I've already written the parsing for it. So it just reads a line and encodes it into hex, then converts it into an integer, and we have these leaks with us. So after the leaks, we are going to jump to start the main. So this time in our program, we'll set up in our debugger, we'll set up a breakpoint there, not the part one. Yep. So we attach to 3772, disassemble main. We're gonna breakpoint here because after our leaks are completed, it's gonna breakpoint at main. So yeah, let's just continue. Put the document in. Just a second. This is what happens when you like write exploits. I don't know why I changed this, but yeah, it's like a very meticulous job. So each byte can pretty much make or break it. So if you don't understand everything about it, it's very hard to debug. So that's why I use these checkpoints in the program so that I can see in the debugger exactly what's going on. For some reason my parsing is not working for that, from what I see. So let's just set up a breakpoint before gets. Just continue. Okay. Okay, so now it works. I guess like it wasn't working because I was trying to hex a string, but anyway. So like we can see that the puts and gets leak are these. Let's just verify in the debugger that are they accurate. So we can see that they are indeed. So our addresses, our leaks that we got from this program are accurate, and now it's again coming in for another round of gets. So now in this round we'll send them the second payload, right? So let's just, actually my program has already sent it the payload. It's just waiting on the gets call. Let me just disassemble main and set it here. Okay, so I'm there now, and this is the second drop chain which comes into picture, the second phase rather. So this is the first phase. We after we get the leaks, now like we yeah, just a second, I forgot one thing. So after you get the leaks, you can go to this libc database. There are like a lot of libc databases. I mean, they've just basically downloaded all the libcs and made it easier for us to find out what version they are, just for these kind of exercises. And we can just put the values in here. So you can see that it matches our libc. And when I check this libc, you can see that it shows us. I mean, you can also get this from pawn tools or read elf or etc. But like it's just easier to just grab these offsets from here. So you can see it just directly gives that a system is at this particular address, and you can also see the puts and gets offsets. And we need the bin sh, so bin sh offset is here. So now I'm just gonna subtract the leaks with like the offsets that I grabbed from there, and add libc base to the system and bin sh offsets I grabbed from there again. These are the offsets I've written. And now it's pretty much the same job. We just need to pop RDI, get the bin sh into RDI and call system. Now we know the exact addresses of those things, so it doesn't really like stop us from doing the attack. So you can see that pop RDI ret is happening, and we can see that what's the value of RDI. RDI is set to bin sh, and it's just gonna call system because it's at ret, and ret on top of the stack is system. So we're just gonna continue, and we see that we have a shell indeed. So we just got done with the second exploit. This kind of summarizes how it works. So we first need to find gadgets to control RDI, which are easy to find using Ropper. In this program, though, we need to print the leaks and then use those leaks to find the libc offsets that we need. So to get the leaks, we use the GOT table and PLT table entries. Using PLT table, we can jump to any function that is used in the program. So the program used puts and gets, so we can pretty much jump to either of those functions. We want to use puts because we want to leak, we want to print out the address values so that we can use it in the program to calculate the libc's base. So that's what we did. This is the offset was 88, and then we did pop RDA. We put the GOT address here, and then we just pass to PLT puts, and after it puts it prints the addresses. We're just gonna jump to main to do another round of this, and then after we have the libc base and all the offsets needed for the system and bin sh and all these things, we can use the second round to get to ret2 system like we did in the earlier exploits. So in the action, it looks like this. We first leak, and then we figure out the libc version using libc databases. And after leaking, in the second round, we just use the same exploit, pop RDI into the bin sh string into RDI, and then just ret2 system. So now finally we are in case 3. This case is a little different, is kind of subtle to spot the differences in this case. The program is a little bit different. We don't use puts anymore, we use write. And as you might know that write has 3 parameters to it. It not only takes 1, it takes 3. And the third parameter is the length. So as long as we don't control the third parameter, it's very hard for us to get leaks using write. So that's why ret2csu is pretty useful in this case. Uh, and like we need to control three registers in this case. We need to control RDI, RSI, and RDX. So RDI and RSI are easy to the gadgets for RDI and RSI to control these are easy to spot using Ropper. Like we have pop RDI and pop RSI gadgets, but the RDX gadget is like nowhere to be found. So, so how do we exploit this program? Because we cannot control RDX to get the leaks, and we cannot really do anything unless we have the registers, right? So this is where exactly ret2csu comes. So ret2csu just adds like a bunch of gadgets that are not shown in a Ropper because of the way those gadgets kind of work. So there is this function. If you compile your library, if you compile your binary with a libc, with any libc, pretty much, you should have like libcsu in it function in your binary, even if you're not using any of the functions. And this function has two set of gadgets that are very useful to control all of these registers: RDX, RSI, and RDI. So you can see that we can just jump to this particular gadget here, and we can pop all of these register values. We still don't control RDX, but just hold on for a second. So after we control all these values, we can then jump to this particular gadget. You can see that RDX is set to R15, and R15 was in our control from this gadget anyway. So that's how we control RDX. RSI is R14, that's how we control that, and EDI is R13, so that's what we control using that. And then we just call at the pointer R12. So R12 is in our control again. So we just need to fill R12 with the PLT table entry that we want to call. R13 is going to be RDI, R14 is going to be RSI, and R15 is going to be RDX. And if we do that properly, we are able to control like three registers and call write with our with the values that we control, and we can leak out the addresses like we did in the last case, even with outputs. So let's jump in the demo. All right, so as compared to our last sample program, this is kind of different. The only change is pretty much that we're using write instead of puts here. So you can check it out in GDB. There's not a lot of differences between the binaries. It's just that the call to this is changed and some offsets might be here and there. The calling principle still remains the same, but instead of having to control only RDI, now we have to control three registers because there's no other way to leak addresses from this binary without using write. So we'll have to control EDI, ESI, and RDX, and to do that we'll use the ret2csu gadgets. So you can do info functions in GDB to find what are the defined symbols. You can see that libcsu init and fini are defined. So I'm just going to disassemble this. This is the pop gadget, the set of pops. So we will be able to write to all these registers, and then there should be another gadget which copies these to the meaningful registers and calls. So 5DA and 5C0. So we can check out the exploit and also run it here. So you can see I've already written down the constants, the addresses to the call and the pop registers, pop gadgets. And we get the got entries in the same way that we did earlier on. So the payload pretty much works as we expected to. We first overwrite the 88 characters, and then we first jump to CSU pops gadget, which will basically pop off multiple values from the stack and put them in registers. So these are those register values, and I'm setting those register values here in just to set up like the arguments and the values of different registers I want it to be. So for the first case, I'm setting it up to write got the RIP, which is like I want to use the write got to execute, and RSI is the second argument, which is gets got. So write second argument is the buffer. So in this case, it will just print out gets got's address, and then we move to the CSU call gadget, which would just move some values of these registers and call. And then we do it again for the other got entry, for the write got entry. So we're printing out gets got and write got. That would give us two leaks for the libc. In the end, we're just gonna jump to main. So I have set up a checkpoint here. Let's set up a checkpoint before we receive. All right. Let's start. So I'm just going to do the same, set up a breakpoint at the last ret to see what we have on the stack to begin with. I'm just going to press continue, and we are here. So in this case, we see that we have the pop gadget right on the stack as we are about to ret, and I'll just open up the exploit while we are looking at this. So the first thing I've put in is 4005DA, which is the address of this gadget. So as you can see, we're just gonna pop different values into these registers. RBX is supposed to be 0, so we're just popping 0 from the stack. Same with RBP. Then comes R12. In our case, we want R12 to be the write got, so it's just an address pointing to the libc address, and in the end the call is gonna basically resolve this address and jump here. So I'm setting up R12, R13, R14 and R15 registers. All of these are now controlled using our input. So you can see that R13 is 1, R15 is 8, R14 is our value that we controlled here. And then after this, we'll jump to the call CSU call gadget. Here we can see R15 is going to move to RDX, RSI R14, and EDI R13. So now we have like R12 set to our write got, and RBX is set to 0, right? RBX is set to 0, and then so this call is just gonna evaluate to R12 plus 0 into 8, and it just points to R12, which is this, just jumps there. So as you can see, we are in write. Now we can press continue, and we are in checkpoint 2. So you can see that the program gets the leaks and calculates the libc base according to the known offsets for this libc. So again, like, we'll just go to the libc database and put these in. You just need to verify what the, yeah, so the symbol for write is underscore underscore write in this particular libc. That's why I wasn't showing when I said the symbol to something else. So again, this is where the libc matches, and we have the different constants, offsets that we can just copy to our exploit. Uh, so I've already filled these in here, and the system is at, yeah, so everything matches. Then we just get libc base using the same technique. Just subtract from the gets offset and gets libc, and then get the other system and bin sh pointers. Then we just need to do a pop rdi ret, set bin sh to rdi, and then call to system. So let's just try if it works. So at this point we are in ret. We're gonna just ret to set the stack properly. Then we're gonna pop rdi, and the top of the stack has been sh. Then we return into system, and we can see the system is getting called. We can continue. So you can see we have a shell. So that was ret2csu in action. And to summarize, we first leak the libc addresses using write call, and write takes in 3 values. That means we had to control RSI, RDI, and RDX registers. For RSI and RDI, we had gadgets in place that we could do that easily. But for RDX, we had to use the ret2csu gadget. Otherwise, it's pretty hard to get around that. And after we control RDX, it's pretty easy to leak the same got entries like we did in previous exploits using write call. And after the entries are leaked, we again put them in the libc database search and figure out what libcs are being used. And then after that, we just find offsets to system and bin sh and use pop rdi to ret to system. So the second phase of the Rop-chain remains the same. The first phase, which is used for the leaks, uses the ret2csu part. That's all I had prepared. Thanks a lot for watching. You can get the repo with the slides and like final exploits and code. It's present at github/lionanish/darkCON ret2csu. You can ask me any questions on Twitter, and I'll be sure to answer them within an hour or two. And you can check out my blog if you need any help on exploitation challenges, or if you're stuck on understanding a technique. I blog about it there. Thanks for watching, guys.